Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. We meet again this morning, this Friday morning. Okay, in this video, I would like to discuss Sidesway frame analysis analysis using moment distribution method. Okay, I want to focus on a frame with one inclined column. Okay, one inclined column. So before we start with one example, with one example, I want to highlight important things in understanding frame with Sidesway. Okay, we focus on one inclined column. Okay, most important thing when we have a frame, okay, like this. For example, this is frame with one inclined column. Okay, what most important thing is we must focus on column first. We will always follow the column. So let's say this is the frame. Okay, and this frame is Sidesway frame. Okay, I want to focus on Sidesway frame first. Okay, this is R prime. Okay, R prime. So we must focus on column AB as well as column CD and make sure in order to identify the delta. In order to identify the data, we must always refer to this concept. Okay, means that the delta must perpendicular with member. This is member AB. So this is the length. Okay, it must be perpendicular. So we apply this concept into frame. We apply this concept into frame. So for member AB, we must find the delta which is perpendicular. Find the delta which is perpendicular. So this is the triangle. Okay. And for member CD, column CD, the delta must be perpendicular with column. This is 90 degree. So this is the triangle. It must be perpendicular. Okay, it moves depending to the Sidesway direction. This is whenever this frame has tendency to move to right direction. Then what happened to beam will just move to this. Okay, the orange is the beam after Sidesway. Okay, the beam after Sidesway. So let's say member AB is actually element number 1. Member BC is element number 2. Member CD is element number 3. Okay, number 3. So we label delta. So we have 3 delta 1 for element number 1, delta 2 for element number 2, and delta 3 for element number 3. So the delta which is perpendicular with column AB is, okay, this is actually the delta. Okay, for member AB. Member AB, delta 1. Okay, which is perpendicular. This is B prime. Okay, look at column CD. Column CD, the delta is called as delta 1 prime. Okay, due to R prime. Okay, for column CD, okay, for column CD, so 90 degree. Delta is horizontal because member is vertical. Delta is horizontal because member is vertical. So this is the delta. This is delta 3. delta 3. So this is C prime. Okay, so we have delta 1 and delta 3. Both delta 1 and delta 3 belong to column AB and column CD respectively. Okay, then only we identify the delta for beam. The delta for beam. And remember, beam is a horizontal member. Beam is a horizontal member. So since it is horizontal, the perpendicular to horizontal is vertical. It means that delta 2, which is belong to beam, is a vertical displacement. Vertical displacement, okay, it is vertical displacement, okay. So from the lowest position to the highest position. From the lowest position to the highest position. So this will be delta for beam. Okay, delta for beam. So if we combine all this, delta 1 prime, delta 2 prime, and delta 3 prime. Okay, delta 3. Delta 3 is this. Okay, delta 3, a horizontal displacement. Delta 2. Delta 2 is a vertical displacement. Delta 1. When we combine, we get like this. This is delta 1 prime. Sorry. Delta 2 prime, vertical, perpendicular with horizontal. So delta 2 is for beam and always for beam. Delta 2 is always for beam. Okay, and delta 3, a horizontal displacement. Delta 3 prime and delta 1 prime. So all this, okay, in all this in this triangular belong to, okay, the delta in the diagram. Okay, so this one, okay, wait. Okay, so delta 1, this is delta 1. Delta 1 is parallel with this. Okay, this is delta 1. Okay, delta 2, this is delta 2, belong to beam. Delta 2 belong to beam. It is a vertical displacement. Okay, because beam is a horizontal member. So this is delta 2. Okay, and delta 3, okay, delta 3 is a horizontal displacement because column CD is a vertical member. Okay, so we combine this, we get this triangular. Means that one inclined column, okay, in frame will produce this triangular. One incline produce one triangular. Okay, so where is this? Where is this in the diagram? Where is this in the diagram? It is actually, okay, so this is actually the triangular. Because, okay, this delta 3 is also actually equivalent to this. This is delta. This is equivalent to delta 3. So this distance and this distance, okay, should be equal. Okay, this and this should be equal. Okay, this is delta 2. So this one is delta 2 prime. So we will focus on this. Delta 1, delta 2, and delta 3. This triangular is very, very important because we will use this triangular, Okay, this triangular whenever we want to find the FEM. Okay, the FEM due to Sidesway. So what we're gonna do is we will assume one FEM. We will choose one member to assume FEM. Don't forget to assume the right behavior. The FEM that we assume must be in right behavior. Okay, in right behavior. Identify where is the triangular. Okay, and then we will focus on this triangular only. Okay, so this is the concept that we need to understand. Okay, let's say we have another frame. Okay, another frame, the same frame. Okay, subjected to R prime in left direction. In left direction. So what should we do? In left direction. Okay. So this is the important thing is we must understand the concept of Sidesway. The delta concept. The delta must be perpendicular. Okay, and we identify from the column. So if we have A, B, C, and D, we have A, B, C, D. Okay, this is frame. This is Sidesway frame. This is Sidesway frame. Okay, we have to mark the delta which is perpendicular to the column. Okay, so for AB move to left direction 90 degree is this. This is the 90 degree. Okay, this is the incline. Okay, and CD move to left direction is this. Okay, so combine. Okay, combine this. We have horizontal, we have incline, and don't forget the vertical is always belong to beam. The vertical measure from the highest position to the lowest position. So this will be the delta for beam. Okay, so the new position of beam is like this. Sorry, not that one. Okay, so we have to find where is the triangular. We just need to combine the horizontal delta, the vertical, and the incline. We just need to combine. Okay, we combine. So horizontal. Okay, we have this and this. So incline as delta 1 prime. Horizontal delta 3 prime. And vertical delta 1 prime. Okay, it is like this. It is like, so if we have, for example, if we have, this is AB is straight column, BC, CD. Okay, fix. We have A, B, C, and D. Okay, again, we have to identify where is the triangular. Okay, we mark the perpendicular. Okay, this is the perpendicular. So we move to this point. And perpendicular to CD is this. So this point. This is perpendicular. So we just need to draw the triangular. Okay. So if we combine delta 1, delta 2, delta 3. So delta 1 now is horizontal displacement. This is delta 1. Delta 1. And then we have delta 2. And then we have, sorry, this is delta 3. Delta 2 is always vertical. This is delta 2, always vertical beam. Okay, 1 is here right now. This is 3. If this move to right direction. Okay, this move to right direction. Okay, and so we have to identify where is this. We have to identify where is this located in the diagram. Okay, so this is actually located at here. And then we need to identify the angle. Okay, we need to identify the angle. Okay, so let's do one example. Okay, one straight to the point. So let's say we have this. Let's say we have this. Okay. And one vertical. Okay. So I just put pose and fix. Pose and is fixed. Okay, so let's say okay, wait Okay, so this is A, B, C, D. Okay, this is frame, this is unsymmetry frame. Unsymmetry frame, so this frame has UDL. Okay, this is 60 kilonewton per meter. Okay, 60 kilonewton per meter. And this frame is tend to move to 300 kilonewton. Move to right direction. Move to right direction. Okay, so distance. Whether the angle is given, you have to determine the distance, or the distance is given, you have to determine the angle. Okay, and this. Okay. Okay, so let's say this is 3 meter. This is 6 meter. Okay, this is 7 meter. This is 2 meter. Okay, let's say this is the dimension, the distance. Okay, so of course, for frame with Sidesway, we have to understand the principle of superposition. Okay, so for that, I hope you can refer to the previous video, because I want to straight away jump to the solution. Okay, jump to the solution. So for the solution, we will have four main procedure. Procedure number one is we will actually calculate K and distribution factor. This will be okay, used in both table 1 and table number 2. Okay, step number 2 or procedure number 2, we will have non-sway frame. Non-sway frame. Non-sway frame. Non-sway frame. So under this procedure, so we have A, FEM due to external loading. Okay, due to loading. B, okay, we have to calculate the end moment, and we label the end moment in table number 1 as M naught. And then step C is to calculate the restraining force, R value. Okay, and then 3, okay, we will continue to analyze Sidesway frame. Sidesway frame. And under Sidesway frame, okay, we will use table number 2. We will use table number 2. So the FEM that we use under Sidesway frame analysis is actually assumption FEM. This is due to delta prime. Okay, due to delta prime. So B, okay, from FEM we will calculate end moment, and the label is M prime. The label is M prime for table number 2. So this one is from table 1. This one is from table 2. Okay, and C is restraining force R prime. And lastly, the final step is, okay, to use the equation that we get from principle of superposition, because we have to calculate the final end moment or the total end moment considering both effect, both external loading and Sidesway and delta. So we have to consider both. Okay, so the final end moment, okay, let's say the label is M final. So this will be equal to M naught, okay, plus R divided by R prime times M prime. Okay, these are the procedure. Okay, these are the procedure. So we move to straight away we move to step number 2. Step number 2, non-sway frame. Non-sway frame analysis. Since this is actually unsymmetrical frame, this is Sidesway frame, so we have to understand the meaning of properly restrained. So we have to make this as properly restrained so that we can remove delta from the main diagram. Okay, we can do that by putting an artificial support at C. Okay, this will be the diagram for step number 2, non-sway frame. So we focus on that diagram. Okay, so this is non-sway frame analysis. analysis. Okay, so what we need to do in order to change this to non-sway frame, we have to put an artificial support at C. So by putting this pin, we will actually change this from unproperly restrained to properly restrained. Okay, the definition of non-sidesway frame, it must be symmetry or properly restrained. Okay, so this is now properly restrained. So by putting this support, so this bring the restraining force in horizontal direction. We want to focus on horizontal direction because this is referring to side sway. Move right or left direction. Okay, so this will bring the restraining force. This is R. Okay, so under this frame, so if we want to complete this, we will have the free body diagram. Means that we will put all the reaction at support A and at support D. So we will do that first. Okay, so at A, okay, at D, okay. Okay. This is AY. This is AX, MA or MAB, MD, DX, and DY. Okay. So the total height. The total height, the height for CD total is 9 meter. So this is 9 meter. Okay. And BC is 6 meter. BC is 6 meter. And AB 3 and 7. So we have to determine the hypotenuse to identify the length of AB. Okay, the hypotenuse. Okay. So it is 7 and 3. 7 and 3. 7 square plus 3 square square root. 7.62. 7.6. 7.62. This is 7.62. Okay, so let's say this frame has, okay, this is 2 EI. This is 2 EI. So this is EI. And this is also EI. Okay, EI is not constant. So 7.62 meter. Okay. So we will continue to do the analysis of end moment using table number 1. Okay, of course, the fixed end moment for this frame will be for member BC only. There's no FEM for AB. There's no FEM for CD. Okay, FEM, okay, is for member BC only. Okay, so we will do the distribution table now. Okay. Okay. So this is the first table. The first table we will focus on non-sway frame. Okay, the FEM will be calculated, okay, using the external loading only. Okay, because we have removed the delta from the system by putting an artificial support at C. Okay, the frame is now properly restrained frame. Okay, properly restrained frame. So as usual in the table, I will do the K or stiffness factor calculation directly in the table. So always remember that K is for element. So whether it is AB or BA, it is actually the same thing. Okay, the same thing. And in this frame, so since I have put BC as 2EI, so we need to consider that. You don't forget. Okay. So length of AB. Okay, since all is fixed end, so we use 4EI, 4EI over L. 4EI over L, so length is 7.62. It is 7.62. It is 4 divided by 7.62. Okay? So we get this. Okay? So for member BC, it is 4 times 2 because it is 2EI. So it is 4 times 2 is 8 divided by length is 6. 6. Okay, this is K for member BC. And for CD, the length is 9. Okay, the length is 9, so it is 4 divided by 9. Okay, it is 0.44. Okay, distribution factor, since A and D are fixed, so DF will be 0, 0. Okay, and then we will start to calculate distribution factor. Okay, divide by total plus this. Okay, we get 0.28282. Okay, I choose to use up to 3 decimal point. Okay, and then for BC, I will get 1 minus, we get 0.718. Okay, so then we continue with CB, divide by total plus, we get 0.75. So another one is 1 minus 0.75. Okay, it is 0.25. So this will be distribution factor, and this distribution factor will be used, okay, in both table. Okay, so FEM. So FEM, refer back to this, it is 60 and 6, WL squared over 12. It is WL squared over 12 for member BC. It is W 60, L is 6, WL squared over 12. Okay, we get this. So this one is positive. One negative, one positive. So we will do distribution as usual. So find the total moment. I put negative to represent the opposite condition of joint moment. So this one plus this times with factor, distribution factor. Okay, it is, okay, I want to, wait, format this first, format cell. Okay, for number, decimal places is 3. Okay, negative, total moment 0 plus, okay, this times with factor. Okay, log. Okay. So we do the same for CB and CD. It is negative 180 plus 0. Okay. Times 0.75. 0.75. I want to log this. Okay. And this with the same process. Plus 0 times with, okay, 0.7, 0.25, 0.25, log. Okay, I have set all to 3 decimal places. That's why I get like this. Okay, so carry over, all is 0.5. Carry over, all is 0.5. So this one divided by 2. Okay, this one also divide by 2. And then divide by 2. Cross boundary, C to B, B to C, A to B, B to A, okay, B to C. It must be cross boundary. Okay, like this. Okay, so copy this formula. I copy this formula and I just paste. Okay, so this is distribution number 2. Carry over. Distribution number 3. Carry over. Distribution number 4. Carry over. Okay, distribution number 4. Carry over. Okay, distribution number 5. Carry over. Okay, maybe continue another distribution. Okay, distribution number 6. Number 6. Carry over. Okay, distribution number 7. Distribution number 7. Okay, distribution number 7. Okay, so this will be n moment. N moment, m not. M not. M not. I will clear the last carryover. Because, okay, we stop at last distribution. We stop at last distribution and then I will total the moment. Okay, total the moment. Okay, total the moment. So this will be the n moment, m naught. Okay, this is. Okay. So this one, I want to copy and put here. Okay. Okay, so this is actually m naught n moment from table number 1. This is belong to non-sway frame. Non-sway frame. So the red color is actually the n moment. There are 6 n moment, 6 member n moment. Start from AB, BA, BC, CB, CD, and DC. Okay. So for verification, so we get MBA plus MBC. Okay, this is MBA plus MBC, which is equal to 0. And we get MCB plus MCD, which is also equal to 0. Okay, this is MB, this is MC. Okay, representing rigid joint B and rigid joint C, the moment is equal to 0. Okay, so from this value, we will analyze R value, the restraining force. Okay, one method to do that is by analyzing this. Okay, refer back to this diagram. So we will calculate or identify restraining force by using shear equation. and shear equation and column analysis. We call it as shear equation because it refers to it refers to the horizontal movement. Horizontal movement because R is in horizontal direction. Okay, R is in horizontal direction. So the shear equation, okay, from this diagram we will write the shear equation. Shear equation. The shear equation is total Fx. Okay, why we do this? Because we want R, and R is in horizontal direction. If R is in vertical direction, so we have to use we have to use Fy. This is Fx because R is in x direction, in horizontal direction. Horizontal direction. So that is why we use Fx. Fx. Okay. So write the shear equation. Write the shear equation. So by looking at this diagram, so this will be the equation. So it is Ax minus dx, okay, plus 300 minus r. This is equivalent to 0. Okay, so r will be equal to, okay, Ax minus dx plus 300. Okay, this will be the equation to calculate R. So there are two unknown here, Ax and dx. There are two unknown here, Ax and dx. So we have to use static equilibrium. We have to use static equilibrium to calculate Ax and dx. Okay, use static equilibrium to calculate Ax and dx. Okay? So how to calculate this? Okay. So step number 1. Step number 1. Step 1. Step number 1 to calculate Ax and dx. Okay, we analyze element CD. If we analyze element CD only, so what we get? We will get like this. Okay, let's sketch it first. So for element CD, so this is CD. This is C, this is D. Okay, this is dx. Okay, this is 9 meter. The moment is moment. CD, negative and negative. Okay, negative. The moment is negative. 70.6. It is 70.6 and 35.3. 35.3. This is 70. Okay, like this. So we will get dx. Okay, by analyzing this. So by taking moment at C is equal to 0, we will get dx. Okay, we will get dx. Okay, the question is, under step number 2, under step number 2, can we get AX directly whenever, okay, under step number 2, under step number 2, okay, if we analyze this, we will have AY, we have AX. Okay, we have moment positive, positive. The moment is positive, positive. This is positive moment. This is positive moment. The value is 40.4 and 80.8. Okay. The question is, can we get AX and AY? Can we get AX? No, because we have two unknown. We have two unknown. So how to get AX? Okay, how to get AX? So okay, we have to create another diagram. Okay, by looking at this, step number 3. Okay, step number 3, what we can do is like this. Okay, this is actually based on the static equilibrium. You can do any step, doesn't matter, as long as you can get AX and AY value. Okay, AX and AY value. This will be one of the steps. Okay, okay, DX. Okay, so if dx is determined in the first step, under the first step, dx is determined. So if we apply, okay, can we apply, okay, this is one of the option. Of course, there are many options. We just use static equilibrium, how you want to calculate AX and AX, DX, AY, DY, doesn't matter. Okay, as long as our aim is to calculate AX and DX. So this is one of the step. Okay, so means that after we calculate DX, we will actually apply in the equation total fx is equal to 0. So this actually will be the second step. This is the third step. Okay, the second step, step number 2, will be total. Okay, can we get AX after we get DX by using shear equation? Cannot. Looks like cannot. Okay, we cannot get that. Okay, can we get DY? Can we get DY and then get AY and after that get AX? Can we do that? Okay, can we do that? So actually we have many options, and one of the option is, okay, like this. Another option is we have to consider this. Means that here is AY, here is AX. Okay, we have moment 40.4, and then we have moment at BC 70.6. This is 70.6 positive. It is 70.6 positive. Okay, we have this step number 2. step number 3, either one. So we will produce equation with two unknown. Equation with two unknowns. Of course, this is 3 and 7. Okay, 3 and 7. And this, okay, 7 and 3 plus 6, 9. Okay, so this one, we have to take moment at B. This is B. Take moment at B, which is equal to 0. So we will get a negative 80.8 minus 40.4. Then we get plus 3ay minus 7ax. Okay, this is equal to 0. So we simplify this, we get 3ay minus 7ax, or we should write ax first, negative 7ax plus 3ay. Okay, this is equal to 80.8 plus 40.4. 80.8 plus 40.4. 1 to 1.2. It is 1 to 1.2. So this will be the first equation. Okay, this will be the first equation. And using the diagram in step number 2, okay, by taking moment at C. By taking moment at C, okay, we will get negative, is it negative? Positive. This is positive. Okay, positive. Okay, it is positive actually. Positive. So what we get is this one positive, this one negative, one negative. Okay, and this, okay, it is 40.4 plus 70.6 plus 70.6. Okay, 70.6 plus 9 plus 9ay plus 9ay, and then minus 7ax minus 7ax, and this is equal to 0. So we get 7ax minus 9ay. Okay, 7ax plus 7ax minus 9ay equal to 40.4 times plus 70.6. It is 40.4 70 Point. It is 111. 111. So this will be equation number. Then we will get AX and AY. Positive. 7AX minus 3AY is positive. Okay. So this will be the two two equation. The two simultaneous equations. So by solving 1 and 2. Okay, solving 1 and 2. So we will get we choose equation with two unknown. Okay. Okay, we get 7, -3, 7, -3, and 1 to 1.2. It is 7 AX -3, 7. Okay, B1 is -3, -3, and C1 is 1 to 1.2. Okay. Okay, now we put the A2 value. A2 is 7. B2 is -9. C2 is 111. Equal. Okay, so we get X is AX. AX is 18.04. Okay, AX 18.04. AX 18.04 meter and 1.7. 1.7. AY is 1.7. AY is equal to 1.7 meter. So what we want is actually AX. AX. So we substitute AX equal to 18.04 meter and DX equal to, okay, not yet calculated. Okay, this is -35.3 minus 70.6 plus 9 dx. So dx is equal to total divided by 6. It is 35. 35.3 plus okay 70.6 divided by 9. 11.77. 11.77. This is okay. 11.77. This is dx, 11.77 kilonewton. Sorry, this is not distance. This is kilonewton. Kilonewton, not distance. Kilonewton. Okay. So it is 11.77 kilonewton. Okay, so we substitute AX and DX in R equal to AX minus DX plus 300. Okay, so we get AX is 18.04 minus 11.77 plus 300. So we get R is equivalent to it is 300 plus 18.04 minus 11.77. It is 306.27. 306.27 kilonewton. Okay, this is the restraining force. The restraining force for table number 1, non-sway frame analysis. Okay, non-sway frame analysis. Okay, so this is part 1. Actually, I want to stop right now. So this is part 1 for this video. So I will continue for part 2 to continue table number 2, Sidesway frame analysis. Okay, so this is actually the 3 step under procedure number 2.